Here's another very interesting reaction that's called aldol addition reaction. Okay, so what is aldol addition reaction? Now this is a ketone that we have over here. So you can generate a nucleophile from the same molecule. So pretty much they both are the same. Do you see that there are two hydrogens on this carbon? And now we know the alpha hydrogens are acidic. So when you add a base, you can create a nucleophile on another carbonyl group, alpha carbon. Okay, or it could be a different molecule or it could be the same molecule. So between the same molecule also aldol addition reaction can take place, or it could be between two different molecules where you can have an alpha hydrogen next to a carbonyl group that can create as a nucleophile and that can add on to the carbonyl group. You'll understand this more when you are looking at the next examples. Okay. So one molecule of the aldehyde ketone is an electrophile and the other is a nucleophile. Okay, so when they condense like that, we call it as an aldol addition reaction. So if you have two molecules of these in the presence of a base, you can have aldol addition product. So where is the new bond is going to form? So here one of these molecules going to form carbon ion like this, a nucleophile. Okay, so then if it is nucleophile that's going to form from here, this carbon is going to connect to the carbonyl carbon of a different molecule. Okay, so when the connection is this carbon, so if you consider this part as here and connect to the carbonyl carbon of another molecule. So this is the new bond form. So basically you started with 1, 2, 3 carbon molecule. If itself add like that, your final product will have 6 carbons. 1, 2, 3, 4, 5, 6. It's a beta hydroxyaldehyde. So, okay. So in the next slide, I will show you how the mechanism works. Okay. The new bond is formed between the alpha carbon and the carbon that was formerly the carbonyl carbon. So this is the alpha carbon that we have over here. This alpha carbon react with another molecule carbonyl carbon. This carbon right here bond with this. At the end, this carbonyl oxygen will become alcohol. So that's what you are seeing here. The bond is being formed between this carbon and the carbonyl. That is that one right there. Okay. And this is between two ketone molecules over here. So one of these is going to form a carbon ion, and then once it is formed, another acetone molecule, this is going to go and react with this carbonyl group. So the new bond is going to form between this group and the carbonyl carbon. Do you see that over here too? So this is from this part over here, and then this is the other part, the other molecule. So the new bond is being formed between alpha carbon and between the carbonyl carbon. The product is a beta hydroxyaldehyde or a beta hydroxyketone. It has twice as many carbons as the reactant. Now this is the mechanism for the aldol addition. Now this is one of the aldehyde or ketone molecule. It should have an alpha hydrogen. So the base normally comes and deprotonate the alpha hydrogen, forming a carbon ion, and this can be in resonance with the enolate. Remember, you know what to do now. So the lone pair goes here, pi bond opens up, so you can have this resonance structure. Now once this is being formed, so this carbon ion are going to react as a nucleophile and going to add on to the carbonyl carbon. So it's going to form a new carbon-carbon bond between the alpha carbon and the carbonyl carbon. Okay, so this is, let me show you. This group over here is this group right there. I mean, along with the alkyl group. Let me put the alkyl group also. This group over here. Do the green color circled part is that, and then this carbon, alpha carbon, is going to connect to the other part, which is this part. So here's the new bond. The carbonyl carbon is this carbon. It has a one hydrogen on it, and then it will become O minus. Okay, do you see the connection, the two carbon-carbon bonds being connected? And then once that is been formed, you form alkoxide anion from a water molecule. It grabs a hydrogen and complete the aldol product, which is beta hydroxyaldehyde. Okay, normally it's called aldol because it has an aldehyde group and also it has an alcohol. Aldehyde, this is the aldehyde group and that's the alcohol, so that's an aldol product. Okay, when the starting material is an aldehyde. And ketone can also do the same. So in this one, we can see if the starting material is a ketone. So this example, the starting material is an aldehyde. Now let's look at if it is a ketone. It's the same thing. Okay. So basically again, so this one also has two alpha carbons. So basically hydroxide can react with any of these alpha hydrogens. Form an enolate anion, carbon ion, and this carbon react with the carbonyl carbon of another acetone molecule. So the bond between the carbonyl carbon, this is the carbonyl carbon bond and this is the alpha carbon, forming an alkoxide anion. Grab the hydrogen from a water molecule. Now we created a beta hydroxyketone. Beta hydroxyketone. So this is your carbonyl group. This is alpha beta. On the beta carbon you have a hydroxy group. So it's a beta hydroxyketone. This is when the starting material is a ketone. Okay. So basically you can consider, let's say you have two molecules of the same. So this is one. Okay. And then you have another one. Carbonyl group. Like that. So if you have two groups, so this carbon over here going to connect to this carbon, form a bond. So and then this bond opens up. So basically this carbon and this is the newly formed bond. And this is the newly formed bond. And this would become OH. Okay, so this is your alpha carbon, this is your beta carbon. So the beta carbon will carry the hydroxyl group where you initially had the carbonyl group and then the substituents that you started with going to be over here. Okay, do you see the connection? Okay. A retroaldol addition is, now if you have a beta hydroxyketone or beta hydroxy aldehyde after the aldol addition, we can get back to our starting material. So retro means reverse. Okay, so how does that happen? Again, this can happen in the basic medium. So when you have a base, so the hydrogen on the alcohol going to be acidic. It's going to grab that hydrogen, give the electrons of the oxygen-hydrogen bond to form a pi bond. Now once the pi bond form, you can see this carbon already has 4 bonds. If it is going to form another bond between this carbon and oxygen, one bond has to break. right? Carbon cannot have more than 4 bonds. So the bond between these two carbons is going to break and give its electron to form an enolate with this carbonyl group. Okay, so once this bond is being broken, you're going to get this molecule from the left side, and for the right side you will have this one. This is the enolate, and then the enolate can become a ketoform, and then when you add water, it can grab the hydrogen and complete the formation of the products that we started with. That is called retroaldol addition. Now this alcohol, the alpha hydroxy ketone or alpha hydroxyaldehyde, we can dehydrate. Dehydration means removal of a water molecule. You can remove the water molecule because you have alcohol group over here, and we can have alpha beta unsaturated aldehyde or alpha beta unsaturated ketone depending on the starting material. Now let's say we have these two molecules of this aldehyde. In the presence of a base, you do the aldol condensation. So now you know what's going to happen. The alpha carbon, which is this carbon of one molecule, going to connect to a carbonyl carbon of the other molecule. Okay. For example, let's see how this is going to happen. So this is the carbonyl. This is one molecule. Okay. And this is the carbonyl carbon right there. CH2, and then this is going to be your R group right there. That is one of the aldehydes, so it's going to form carbanion right there. And then from the other one, you have a carbonyl group over here, CH2R group, and then you have hydrogen over here. Now, how is the bond going to form? Now, the bond is going to form between here, right? Nucleophilic attack. You are going to form a bond, and then the carbon-oxygen bond will open up. I'm not drawing the mechanism, I'm just showing you how the bonds is going to form a connection. This is not a mechanism. I'm just showing you where the connection going to happen. Okay, so then you can draw the new molecule. You have your R group. This would become OH, and then the hydrogen will be there, and this is the new bond that's been formed. R group going to be there, carbonyl group over here, hydrogen over here. That is the same molecule drawn over here. Carbonyl group with the hydrogen, CH group. So this here CH group, this is CH having your alkyl group down here, and this is the other one, CHOH, CH2R. Okay, so once you know how the connection take place, when you are given with two aldehydes, two ketones, or two different molecules, you know what are the products of the aldol addition. Okay, it's going to be a beta hydroxyaldehyde. In this case, this is the structure. Now, once you get this alcohol, we can remove a water molecule. What is water molecule consist of? H2O. So OH group and a hydrogen. So OH comes from here, and then the hydrogen goes from the neighboring carbon, which is need to be alpha carbon carrying the alpha hydrogen. That's the hydrogen that's going to lose. Okay, because when the dehydration take place with these two carbons, you will see that it has added stability because it's an alpha beta unsaturated aldehyde. But if it is going to form, if the OH group going to go from OH group along with the hydrogen from this carbon going to go away, then it would not create that conjugation. Okay, and with this hydrogen it forms alpha beta unsaturated aldehyde, which is an enone. Conjugated double bonds are normally more stable than the isolated double bonds. Okay, they are stabilized through resonance. So the overall reaction is called an aldol condensation. So once you get the aldol product, aldol addition product, After removing a water molecule, when you get the alpha beta unsaturated carbonyl compound, we call that whole process as aldol condensation. A condensation reaction combines two molecules by forming a carbon-carbon bond. We did that, carbon-carbon bond, while removing a small molecule. The small molecule left here is a water. Sometimes alcohol can also be lost. Okay, so this whole process is called aldol condensation. Now, in the presence of a base, how do we remove a water molecule? This is the base catalyzed dehydration of an aldol addition product. So this is the aldol addition product. When you have a hydroxide group, we have seen this one before. So hydrogen will be lost by the base and then form a double bond, carbon-oxygen carbonyl group, carbon-carbon bond break, and then form these two molecules. And then you can form the this is the enolate ketoform, adding water, regenerate the molecule that we started with. Okay. Now, so this is the forward reaction. So you have two molecules of these in the presence of a base and water. We can get the aldol addition product, which is a beta hydroxyaldehyde. When you heat it up in acidic medium, so according to this mechanism, we just saw the mechanism, the same mechanism, it loses the water molecule OH and the hydrogen to form alpha beta unsaturated aldehyde enone. The elimination reaction is called E1CB. What is E1CB stands for? Who know what is E1CB? It is a conjugate base, unimolecular conjugate base elimination reaction. Okay. So this is the mechanism for the E1CB reaction. So the hydroxide take the hydrogen from the alpha carbon instead of getting it from the alcohol, form carbon ion. Now carbon ion is resonance stabilized like this. Give the lone pair to carbon-carbon bond to form a pi bond, and then the pi bond in the carbonyl group opens up. Okay. Now once this happened, you can see there is a nice flow of electrons. So one of the lone pairs reform the carbonyl compound, pi bond breaks, give another pi bond over here, and then the hydroxide group lost. So we're gonna make that condensation product, which is alpha beta unsaturated carbonyl compound. So this is the mechanism E1CB. Okay, E1CB reaction occurs when the carbon ion can be stabilized by electron delocalization. See, it has a stability due to the electron stabilization. So if this is possible, then it can undergo E1CB mechanism. In some cases, we can see that the dehydration product is the most stable product. Pretty much the alcohol form will not stay long. It will quickly remove a water molecule without any additional effort and reform the alpha beta unsaturated compound. That is when the pi bond or the carbonyl group is further stabilized through the conjugation to the benzene ring. Okay, it has an added stability due to that extended conjugation throughout the benzene ring. Now for example, this is benzaldehyde. So benzaldehyde, when it condenses, now you know how the bond is going to form. So if you recall, so we only have alpha hydrogens on this side. There are no alpha hydrogens on this side. Okay, so the connection is going to happen like that. So on this side you have the benzene ring and then CH3. right? So this carbon right there, CH3, going to form a carbanion, and from the other side you have this benzene ring, and then the carbonyl group and the methyl group over here. Okay, so you're going to form the bond between here. You're going to form a bond. Okay, and once the bond is formed, this is going to open up. So the molecule that is going to form is, you have benzene ring, this would become OH. This will still carry that methyl group. The bond, new bond is being formed with that carbon, and then the carbonyl group, and then the benzene ring. You see how the aldol product is being formed? So it's the same thing that you are seeing over here. Okay. Benzene ring, carbonyl group, CH2, and then the carbon with alcohol. Okay. And once this is being formed, so this is put in square brackets to indicate that it is highly unstable. So here we have hydrogen on this carbon. It removes a water molecule to form alpha beta unsaturated carbonyl compound. Losses water without catalyst or heat because the new double bond is conjugate with the carbonyl group and the benzene ring. The more stable the double bond is, easier to form. Okay, so this double bond excuse me, have extra stability due to the conjugation with the pi bond, pi system of the benzene ring. You see, it's a beautiful conjugation. So you can draw steps for each one. Okay, so that is why it happens without any catalyst or heat in the reaction mixture. Excuse me. Crossed aldol addition forms 4 products, meaning if you are going to react A and B, so in A we have alpha carbon here with alpha hydrogens, and we don't have any other alpha carbon or alpha hydrogen. This is not alpha hydrogen. Okay, and B also we have alpha carbon with alpha hydrogen. So what are the possible products that we can form? We can form carbanion with this carbon and can add it on to this carbonyl group. Or we can form the carbanion here and add on to one of the same kind. Or you can have carbanion here and add it to the same carbonyl group. Or you can form the carbanion here and add it on to the carbonyl group of the different molecule of this kind. So likewise, there are 4 types of cross aldol products are possible. Okay, so let's see. In this one, when you add the base, let's say you form the carbanion on this carbon, so you form that, and this one can self-condense with another molecule of this molecule with A, and then what you're going to form is this molecule, because this carbanion react with this carbonyl group. So this is the product for that. And when you add water, it's going to grab a hydrogen and then form alcohol, aldol product. And then the same thing, once you form the carbanion, it can react with B. B carbonyl carbon. So then you have this part from A and this part from the B, and then can give the aldol product. And similarly, if you deprotonate this alpha hydrogen, it's going to form this conjugate base, which is the enolate ion. This can again react with one of the A molecules and form this one. Or B can self-condense with another B molecule and form this compound. So there are 4 possible products from crossed aldol addition having only one alpha carbon for both of these molecules. Can you imagine if you have another alpha carbon over here, another alpha carbon over here, how many products you would get? It's going to be a mess. A lot of different products, right? So in your leisure time, try to understand how the connections are being made. What are the 4 possible products that you can get from this condensation? So obtaining one product from a crossed aldol addition. So you saw the complication that we have, if you have many alpha carbons, and then what are the possible products. So but if you want to form one compound, what do we need to do? So let's see what we can do. So let's say you have this carbonyl group. This is benzaldehyde molecule. Do we have any alpha hydrogens in this molecule? Alpha hydrogens? No, we don't. Because alpha carbon is right there, but this carbon doesn't have any hydrogens on it. This carbon is already having 4 bonds. It cannot add any more hydrogens. And this hydrogen is not alpha carbon or alpha hydrogen because it directly adds on to this carbonyl group. So we're going to react this with this compound. And here also we have only one carbon carrying alpha hydrogens. Because this carbon has 3 methyl groups, it doesn't have any alpha hydrogens either. So it's not going to be that hard in this case, since we have only one alpha carbon carrying alpha hydrogen. So you add this one slowly and then create the enolate here. But there is a challenge because this can self-condense with the same molecule. So that's why we are adding slowly, meaning at a given time in your reaction flask, we have only less number of molecules of this compound. What happens if you add too fast? You're going to have more concentration of this molecule. So once it forms the enolate, it can self-condense because this carbon can react with another molecule of the same and can have a cross-condensed product. Now adding slowly, you generate the carbon ion here. Once it forms, it can go and attack to this carbonyl carbon. So the new molecule is going to be forming the bond between this carbon and the carbonyl group, carbon and the carbonyl group, OH, and then it can immediately lose a water molecule because it has added a conjugation with the benzene ring. So you're going to get this molecule. And this one is called Claisen-Schmidt condensation. The carbonyl compound with alpha hydrogens, added slowly to a solution of the carbonyl compound without alpha hydrogens and a base. Okay, this carbonyl compound doesn't have alpha hydrogen, and also we need to have a base. So the base will help to deprotonate the alpha hydrogen from this compound. Here's another way, another example that we can see how to obtain one product from a crossed aldol addition. Okay. If both carbonyl compounds have alpha hydrogens, now you can see here, this is alpha carbon, this is alpha carbon. Now we're going to react this with this compound. This also have alpha carbon. So you add LDA. It's a strong base. It forms the enolate. Once you form the enolate, you're going to add this one slowly. When you add slowly, we already made the enolate with this one. We don't want to make an enolate with this guy. So then this is made to react with the carbonyl carbon of this one. So the connection is going to be between this carbon and this carbon, making the alcohol. Okay, enolate is first formed in the reaction flask and then you add this one slowly. LDA is used to form the enolate ion and the other carbonyl compound is added slowly. I hope you understand the reason, because this can also form an enolate because it has alpha hydrogens, but we don't want to do that. Using retrosynthetic analysis to determine the starting material. Now let's see if you are given a compound and asked how you can make this molecule. If you see a compound like that, which is alpha beta hydroxy, a carbonyl compound, we know that we can use Aldol reaction to get this one. And now we understand in Aldol reaction, the carbonyl carbon, so this is the carbonyl carbon, next to that alpha carbon going to form a bond with the carbonyl carbon of the other compound. So this bond is being formed by the aldol addition. So basically if you break that bond in your mind, what you're going to get is these two compounds. From this side you have this aldehyde, and from the other side you should be seeing in your mind you have a carbonyl group, and then with this hydrogen, that is an aldehyde. Okay, and then you can see, okay, I'm going to mix these two together to do the synthesis. So we need to make carbanion here. So you take that. So see, there are two different kinds of aldehydes, and then we know we need to make the carbanion with this aldehyde. So you take that, react with LDA-THF. So you can form the carbanion over here, and then the other one you add slowly. Okay, so then this is going to go and add on to this carbonyl carbon and form the alpha hydroxy carbonyl compound. LDA used to form the enolate ion, and the other carbonyl compound added slowly. Another molecule, retrosynthetic analysis. Now, excuse me, you can see here, we don't have an alcohol, but here we have alkene, which is alpha beta unsaturated carbonyl compound. Alpha beta unsaturated carbonyl compound. If it is unsaturated to begin with, you know that is that could be due to the loss of a water molecule after the aldol addition product. Now where would you keep your OH? OH going to be on the beta carbon. Okay, and then the hydrogen is on the alpha carbon. So you put the water molecule back. So that is we are going back to see how can we get this one to work. So it's a beta hydroxyaldehyde. So then we know, if you remember the aldol, so this is where the connection between the two aldehydes or the two ketones. So from this part, from the right side, what we have is this part, COH, and then there are 1, 2, 3 carbons long. Alpha carbon, okay, so these 3 over here. Okay, so that is this 3 group. And from the other side, you have a methyl group, carbonyl group, and a hydrogen. This group. Right? So where are we going to make the enolate? So the enolate has to be done on this carbon. So you take this molecule over here, you add LDA to form the enolate, and this react with slowly with acetaldehyde, which is this one, to make the alpha beta hydroxy aldehyde. And then when you heat it in the presence of a acid, you can have the alpha beta unsaturated aldehyde. So that's the retrosynthesis, meaning going back and see how we can get the forward reaction. If you are given a starting product, and find out how would you synthesize this molecule. Okay. Okay, so I think this is enough for Aldol. We'll start the next session in the next section.